Okay, so we start with Strowger's automatic phone exchange. And the interesting thing is not just the exchange, but the story behind it. Almon Strowger was an undertaker in Kansas City. And his main problem is that the switchboard operator, whenever somebody called and asked for an undertaker, directed the clients to a friend of hers and not to Strowger. And there were only 2 undertakers in Kansas City, and all the business went to Strowger's competitor. So Strowger's idea was, he got so mad that he decided he'll invent a machine which will put all phone operators out of a job. And if you recall from the old movies, the phone exchanges were a matrix of jacks, and the phone operator would plug in the jacks according to the destination of the call. So Strowger, who had no technical education whatsoever, but he was obviously a genius if he could come up with that, he figured out he'll imitate the motion of the phone operator by building a miniature matrix of connectors and having electromagnets do the work of the operator. But in order to realize that, he had to invent many things on the way. So he is the first one who thought of the idea of a phone dial. And here is a phone dial, which actually didn't change at all from Strowger's days. So when you turn the dial, it sends electrical pulses. I'll just let it go back slowly so you can see. If you watch here, you can see as the dial goes back, it opens a contact. The reason it sends the pulses on the way back and not when you pull it is that this way it can have a constant rate of pulses, because if it sends the pulses on the winding up, each person would pull it at a different rate. But the return rate is constant. So Strowger thought of that and made a dial which makes the pulses. And then he made a mechanical motion with electromagnets which mimics a phone operator by moving in 2 dimensions. So if this is a phone and this is a 100 customer exchange, the first exchange was just 100 phones. So when I dial the first number, it will go up to the right row. When I dial the second digit, it will turn to the right column. And this way it selected the right connection out of the 10 by 10 matrix. And when you hang up, it will go back to 0. So this was invented in 1888. And Strowger was quite a good businessman, not just very clever technically. Imagine, it's quite a complex thing to come up with in 1888. He formed the Strowger Automatic Telephone Company, which later on merged and became the Automatic Electric Company, which merged again. But the traces of his company still exist today. And he started manufacturing dial phones and these exchanges. This design lasted 100 years and more. There is many places in third world countries, like in Africa, where this is still the phone exchange. If you want more than 100 phones, obviously you need more of those. One selects the first 2 digits, the next one selects the next 2 digits, and so on. The most surprising thing about Strowger's story is that 10 years later, when the business was successful and the phones were successful, he sold his shares in the Strowger Automatic Phone Company and went back to undertaking, which he did the rest of his life. Okay, so the next thing is Edison's invention of the phonograph. Of course, everybody knows Edison because of the light bulb. By the way, this is an Edison light bulb, an original Edison light bulb with a carbon filament. And you can see a sign that the Edison company put on the light switches, warning people not to light them with a match. But Edison's most original invention, which really came out of nowhere, was the gramophone. The reason I'm saying this, because some of you may not know, that there were houses lit with electric lighting before Edison. For example, in England, Swan had already light bulbs on sale and houses lit by light bulbs a couple of years before Edison. The contribution of Edison to the light bulb was actually that all the light bulbs before him had to be wired in series because they worked on low voltage. They had a metal filament, they needed a low voltage. So if one light bulb burned out, all the light bulbs in the house burned out, like in a Christmas tree when the light bulbs in series. So Edison is the first one to understand and to implement a system where the light bulbs are connected in parallel, because he realized that's the key to selling an electrical lighting system. And that's why he worked so hard to find a filament which has a very high resistance. So the light bulb can be plugged in into 120 volt. At the time it was DC, later on became AC. So he contributed enormously to the light bulb and to the distribution of electricity and to everything to do with lighting, but he basically improved a known idea, improved it a lot. But the thing he came up with, where there was no precedence and was totally like magic, was the phonograph, because it was the first time in history a person could hear his voice, or a piece of music could be kept for eternity, because people could see what they looked like ever since creation, because you can always look in the water and see your reflection, or somebody could paint you. But nobody knew what they sound like, and if there was any piece of music, of course, you couldn't capture it. So Edison came up with this machine which engraves a cylinder from the vibrations of the sound. The original cylinder in Edison's machine was actually tinfoil. Later on, it was changed to wax. So it was actually changed to wax by Bell, the phone inventor, and some others, because the wax was more durable, easier to engrave, and more durable in playback. So I'll just show you what it sounded like. So it had a wax cylinder which rotated, and it had a diamond needle which followed the groove, and it was all mechanical. There was no electricity connected to it. That's why it needed a big horn to amplify the sound. So you can see, if you play it, and that is the first time in history that people could actually hear recorded music, which was an astonishing thing. Now, there's a few interesting things about it. This machine could also record, not just play back, because if you sang into it, it could scribe the wax and record. The only difference was there was a special needle which was sharper, sold for recording, and another needle sold for playback. And the needle is exchanged very easily. All what you have to do is open this screw, and this whole piece comes out, and you can exchange it. So if you exchange this to a recording head, you could record. Obviously, it's better to have two heads, otherwise when you play music and somebody talks, the talk will be recorded together with the music. So it's better to have a system where one head records and one head plays. Now, there were millions of those things made. So this thing, although it's old, this was invented in 1877, just before the light bulb, and was very, very popular from the start, and there were millions of those cylinders made. To show you how common they were, when I got this and I restored it, I said, is there a chance I can get klezmer music on Edison cylinders? And a 5-minute search on eBay came up with several klezmer recordings made 150 years ago, roughly, for the Edison thing. You can get any piece of music you can think of, still available today on Edison cylinders. And the reason why you can get this is people just store these things in their attics, and they were hidden there for generations. And then, even recently, some boxes of those things are being discovered. So there is endless music available on these wax cylinders. So again, this was 1877, just before the light bulb invention, Edison's phonograph. Okay, so the next thing I want to talk about is Ted Maiman's laser. So Ted Maiman is actually one of the few inventors I'm talking about that I had a personal connection to, because he and his wife Kathleen moved to Vancouver and we became good friends. And this is actually not the world's first laser, but the second, because his widow, Kathleen Maiman, has the first laser, but luckily he had spare parts to make a second laser, which is exactly the same as the first one. But before I talk about Ted Maiman's laser, I want to say a few words about Ted Maiman's father, Abe Maiman. So Abe Maiman worked for Bell Labs in the 30s. And at the time, there was a great need for a product which will allow people to listen to radio while they're driving. Today it sounds very simple, but in the 30s, the radios were tube radios. They all needed a high voltage DC. Like at home, they worked either from batteries or rectifiers. But in a car, there is at the time was only low voltage, 6 volt, and the radios needed about 200 volt. Now, if it is AC, you can use a transformer to boost the voltage. But if it's DC, at the time, there was no electronics available to boost the voltage. So Ted Maiman's father, Abe Maiman, had this idea of something called a vibrator, not to be confused with what is today called a vibrator, which is actually much more ancient than that. So in Ted Maiman's vibrator, there was a coil which put into a resonance a blade, and that blade had sets of electrical contacts. And the first set of contacts converted the DC, the 6-volt DC of the car, to AC. Then it was run through a transformer and then converted back to DC. So if you took this thing plus a transformer, you can get any DC voltage you wanted, and you can listen to radio while you drive, which was a huge thing. However, Abe Maiman showed this to his friends at Bell Labs and asked them, should I patent it? And they said, who would want it? You know, who needs to listen to radio when they drive? So he dropped it, and of course they talked him out of endless millions, because later on Motorola invented it, and they made endless money on putting radios in cars. The name Motorola comes from motor radio. That was their business, basically, to put radios in cars. So it's a bit unfortunate that Ted inherited some of the genius from his dad, but also he inherited some bad business sense, as you'll see in the rest of the story. So this is Ted Maiman's laser, and I'll just open it up to show you how simple it was. So what it has a flash lamp inside with a cylindrical reflector. It has a ruby crystal, and today lasers are made that one side of the crystal is fully mirrored and one side is 99% mirrored, so the light can come out. At the time, Ted didn't even have a ruby with a 99% coating, so he took a regular mirror and scratched out the middle. So the middle is only 1% of the area, so 1% of the light can come out. And that's the whole thing. Now, this thing lased first in May 16th, 1960. And matter of fact, here is the page from Ted's notebook, and you can recognize in the picture the laser, which is this. And it's charged up with a capacitor, and he's looking for the lasing. And at some point here, as he increases the discharge, he makes a question mark whether this is it, whether it's lasing. And indeed it was. It was the first time that it lased. So what he did, he put in more voltage in the capacitor, which caused the flash to flash. Because at a low light level, the crystal just fluoresces. It doesn't laze like fluorescent paint. But above a certain level, lasing action starts, and that's indeed where the laser was born, May 16, 1960. And what is surprising about Ted Maiman's laser, that it went against all common wisdom. Because at the time, people believed the best way to make a laser is using gas. So you had a long tube full of gas, and then you have to put in energy into the gas. However, Ted understood that the gas doesn't have enough molecules, so you need to put in a lot of power to make it laze. this power will cause distortion in the laser, and he understood it would be a difficult way, and indeed it took several years later until somebody could make a gas lathe. So he thought of a few things which were contrary to common wisdom. First of all, he said he has more chance to make it from a solid material rather than a gas. Secondly, he understood the problems of heating and distorting the laser, so he said the best chance is to make it a pulsed laser, because in a pulsed laser, it only lasers when the flashlight goes off, and it doesn't have a chance to heat, because the pulse is so fast. So you don't have to worry about distortion from heat. And the third thing where he went against all common knowledge was to use ruby as a lasing material, because ruby was actually used in the predecessor of the laser, something called maser. That was a microwave laser. And there was many articles about ruby, but people did an analysis if ruby can be used for a laser, and the conclusion was it can't. Without getting into the technical stuff now, it was known that ruby cannot be used for a laser, but Ted Maiman, who worked on ruby after his PhD, he had a very good intuition for the material, and he didn't believe the papers. So he had a technician working with him, and he told him, I don't trust the papers. I want you to redo all the measurements these papers claim they did, and tell me if indeed this material cannot lathe. The technical term is, does it have enough internal gain to lathe? So his technician went and did all the measurements and came back and said, Dr. Maiman, sorry to tell you, all the published papers are correct. The ruby cannot lathe. But Maiman didn't even believe his own technician. So he went and did the measurements himself. And in doing the measurements, he realized that the way everybody was measuring it was completely wrong. I mean, the results were correct according to the test, but the test was the wrong test. And then he tested it the way it should be tested, and he realized that ruby is one of the best materials for a laser. And from there, it didn't take very long. The whole thing was done on a $50,000 budget in 9 months. His bosses gave him this limitation because, as they said, they want him to work on something useful. But since he insisted, they said, okay, you got 9 months and $50,000. And he did it in those 9 months and in this budget, while others spent millions and years. It's also surprising he didn't receive the Nobel Prize for it, because everybody who made improvements to the laser got the Nobel Prize, and the people who wrote the theory of the laser but could not build one, Townsend Shelov, got the Nobel Prize. But Maiman, who really made an excellent laser and the first one to lathe, didn't get the Nobel Prize. And there are many theories about it. Of course, the archives of the Nobel Committee are sealed, so nobody knows the real reason. But the speculation is that Towns, who wrote the paper on the laser which got the Nobel Prize, was very jealous that he couldn't build a laser and Maiman did. And since the previous Nobel winners have the first right in the committee to judge new candidates, the speculation is that Towns told the committee that what Maiman did wasn't very important, and therefore he didn't receive the Nobel Prize. But it's a speculation. It's still a mystery. There are, in the history of Nobel Prizes, there's a few strange cases like that, and nobody will really know what went on. Okay, so that's the history of the laser in short. The next person I want to talk about is Fritz Haber, and also Fritz Haber and his partner Carl Bosch. Both got the Nobel Prize for what they did, and unfortunately I couldn't really get any exhibits from Fritz Haber. The only thing I could get which belonged to Fritz Haber was a strange thing. It's a medal that he minted of himself, and as he used to use as a gift to his friends. It says on the other side in German, with heartfelt thanks, Fritz Haber. Okay, so he was a bit of a strange person, even as evident by minting a medal of himself. But he invented the thing which is probably the most important thing in human history. And it's interesting why he is less known after inventing such a thing, and why Carl Bosch is totally unknown. So at the beginning of the previous century, people were trying to find a way to bind nitrogen into a molecule which can be made into the two most useful things people were looking for 120 years ago. One is fertilizers and one is explosives to kill each other. So both fertilizers and explosives rely on a molecule which contains nitrogen. Now the air is full of nitrogen, but nitrogen is pretty inert. It's very difficult to bond it to another atom, so you can then make compounds which are nitrates. The main source of nitrogen until Haber's invention was basically a material called guano. And guano is basically bird droppings. As many countries in South America, especially Chile, has big dry areas which were covered by a thick layer of bird droppings, and because they are arid, there is no rain to wash it away. So over thousands of years, this layer covered big areas, and all these countries were exporting this material, which was as strategic at the time as oil is today. So when a war broke out, the first things countries did, they tried to block the shipping lanes for guano, because they knew without guano you can't make explosives. And in good times, of course, needed it for agriculture. So there was a competition among all nations and all scientists to find a way to make artificial nitrates. And as I said, the way to nitrates is to bind the nitrogen. And one of the ideas was to bind nitrogen with hydrogen, because nitrogen was available from the air, and hydrogen is very easy to make. So the idea was to bind nitrogen and hydrogen into ammonia, because once you have ammonia, you can generate other nitrogen-bearing compounds. So once you manage to bind the nitrogen molecule, the rest is easy. You can convert it to nitrates, you can convert it to many other useful chemicals, but the first step is very, very difficult. And the difficulty is really in the yield. You can show an experiment in the lab that you bind some molecule of nitrogen to hydrogen, but if you try to scale it up, the yields are very low. And strangely enough, it is possible that the reason that Haber invented it before anybody else, that he, as I hinted before, he was a bit arrogant, although he was a bad husband, but actually not a bad person. And he was very sensitive to his honor and reputation, and he wrote a paper about his experiments in binding nitrogen, and there was probably some error in the measurements, because he claimed in this paper that he was getting, say, 1% ammonia, which was considered very high yield. And it's doubtful whether he really was getting it. So some other professor wrote a critique of this paper in very nasty language. And he said, Mr. Haber, better learn how to do measurements and learn how to calculate. Haber was already a professor at the time. And Haber was personally insulted. And he decided to work day and night to improve the process in order to really reach the yields he claimed in that paper, probably by mistake. And when you are driven by ego and you have the personality of Haber, there is no limit what you can do. So he worked very hard and indeed managed to improve the yield even better than this paper. And then he published another paper showing that the guy who wrote critique about him didn't know what he was talking about, and he was very happy. But at the same time, he understood the immense potential of his process. The key, by the way, to the Haber process is the right catalyst. And it turned out, surprisingly, that the best catalyst for the Haber process is a contaminated catalyst. For example, iron oxide, which is rust basically, is a much better catalyst than pure platinum or pure iron, or all the pure materials were tested. And in the early days, all the researchers tried the purest catalyst and couldn't get results. And in one test, there was some contaminated catalyst, and it produced much better results. And eventually people understood that it's actually the impurity in the catalyst which make it better. But Haber figured out very quickly in which direction to go and came up with a process which showed, at least in a lab model, promising yields. However, it was a very, very difficult process to scale up. And the reason is that this reaction happens at 200 atmospheres and at 500 degrees C. Now, you can make a steel tank to hold 200 atmospheres, but it's hard to make a steel tank which can hold 200 atmospheres at a temperature of 500 degrees C. And on top of it, at the time, nobody knew that the presence of hydrogen destroys the strength of steel. So all the early tanks they built, after a short time, exploded. And it was actually Carl Bosch, who was, at the time, at the head of BASF, the German chemical company, that committed to solve all these problems and make the Haber process a large-scale success. Now, this is as big an achievement as Haber's achievement, because everybody in the chemical industry at the time said it's not going to be possible to build a reactor which works at 500 C and 200 atmospheres, and they had huge explosions at much lower pressures and temperatures. But Carl Bosch, besides being very smart, was also a metallurgist by training, and he did an amazing job on spending years analyzing the problems and how to solve them with absolutely ingenious solutions. He's actually the father of high-pressure chemistry, because later on a lot of other reactions were done under these conditions of high pressure and high temperature, and it's a very good way to generate different chemicals. So in the Haber process, he personally committed to the board of BASF that he will guarantee they'll solve all the problems, and indeed they did. And he got the Nobel Prize for his part. Haber got the Nobel Prize in 1916, I think, and Carl Bosch got it in 1931. The process itself was invented in 1909. Now, what is interesting, if you look at the graph at the world population, the limit to growth historically was food. And once you could make as much fertilizer as you want, the world population started growing very fast. So if you look at the graph at world population, the knee, the point where the graph changes direction, is around 1910, 1920, where the Haber process was mass-produced and there was as much food as you wanted, unfortunately as much explosives as you wanted too. Now, Haber is also a very interesting personal story, and the reason he's not well known is because he was also the guy who invented gas warfare. In World War I, he was Jewish. His parents were Jews from Poland, but he saw himself as a proud German and was made an officer in the German army in World War I, and he introduced poison gas. And he was very patriotic German, and he didn't listen to any criticism that it's not human and all this. He said, if you die, you die. It doesn't matter how you die. And most world scientists came out against it, that he worked on poison gas. And again, as an unfortunate twist of history, after the war, Germany, of course, wasn't allowed to work on poison gas. So he worked on poison gas to kill insects and rodents. And this was in IG Farben. He had a research institute, and they developed Zyklon B, which was the gas the Nazis used to kill the Jews. And actually, Haber's family was gassed with this gas in World War II. And it's interesting, when I was a young kid, or a high school kid, I worked in the Weizmann Institute in Israel, and I saw there was a Haber library and a Haber lab, but it was locked. Nobody could go in. And I never understood what it was. How come there is some Haber library in Haber lab, while Haber was never in the Weizmann Institute, he never was in Israel. And it turned out that after he was dismissed from his position and everything by the Nazis, after much soul searching, he listened to Weizmann and Einstein and decided to come to Israel. That was in the 30s. He sent ahead his lab and library, but he died on the way. He died in Switzerland, and that's why there is a Haber lab and library, but there was no Haber in Israel. So Karl Bosch also was a very, very interesting person, besides having very high achievements in technology. Karl Bosch was a vocal anti-Nazi. So when Hitler came to power, he was dismissed from all the high positions he had, and slowly found himself lonely and rejected. And he died of cancer, I believe, in 1940, quite at the age of 65, I think. But what is amazing is that before he died, he left a public letter. And in 1940, everything looked great in Germany. But he wrote a public letter outlining what will happen to Germany during the war. And it is chillingly accurate. For example, one of the things he says there, that Hitler will not resist the temptation to attack Russia. And he also describes step by step how things will look good at the beginning and then how things will deteriorate and how all of Germany will be ruined because of Hitler. But he had an amazing foresight, because he describes step by step at a time where nobody could imagine that things will go wrong. He describes in great detail the downfall of Germany because of Hitler. And at the time he knew he was dying, so he wasn't afraid to publish this letter, because this was just on his deathbed. Okay, so I have quite a few things from history of telegraphy. The first thing I want to show is some historical pieces from the first transatlantic cable. Because if you lived in 1850 and you wanted to arrange some deal or some meeting with somebody in the United States and you were in England, everything took a month, because you sent a letter which went by sailboat in 2 weeks, and then you got an answer which went by sailboat in another 2 weeks. So the pace of things couldn't be fast, because every step was a 1 month delay. So imagine an email system where there's a built-in 1 month delay for each email. While inside the countries, telegraph was already widespread, because Morse telegraph started spreading around 1840. So by 1858, there was already Morse telegraph over land everywhere, but there was no connection between Europe and the US. And the two people responsible for the success of this connection were Cyrus Field, who actually laid the first transatlantic cable, and Oliver Heaviside was actually the person who made it work, because he understood why the first cable didn't work. So this was a piece from the first transatlantic cable with a certificate signed by Cyrus Field with a picture showing that this is a real thing. The piece of it was basically it was so revolutionary that everybody was so excited that the cable was laid that Tiffany sold these pieces of the cable as commemoration for the successful laying of the cable. Many people didn't believe a cable can be laid across the ocean, and they were almost right. The reason why there are so many places in British Columbia which have the name telegraph in the name, like Telegraph Road, Telegraph this, Telegraph that, there was a backup plan to lay a cable across the Bering Straits. So the backup plan was to lay a cable from London through Siberia through the Bering Straits, down through Canada and to San Francisco, and from that to New York. Because the purpose was to link New York and London. And one of the big stations for this cable was supposed to be New Westminster. And indeed, if you look at a newspaper, when the second cable was successfully laid, that's a newspaper from the day the second cable was laid. It shows you the two cables, one which goes through the Bering Straits down to New Westminster, and one which goes through the Atlantic, because they were both laid in parallel because people didn't really believe that the Atlantic cable will succeed. Matter of fact, the cover page of this newspaper has a picture of New Westminster and says, New Westminster is the capital of BC. So that was the cable. It failed because people didn't listen to one person whose name was Oliver Heaviside, again, a person who deserves a lot more recognition than he got, because he developed the basic things in telecommunication, but he was self-taught, he was a recluse, was half-deaf, he didn't communicate well with people, was very sarcastic. So because of that, he, except for a few things named after him, like the Heaviside layer in the atmosphere and the Heaviside transform in mathematics, there was not much left of his heritage, which is a shame. Because without getting into technical things, he's the one who really understood how to make a cable which works, and people didn't believe him. And it took many, many years that people really realized he was right. Matter of fact, AT&T wanted to pay millions for him to patent his ideas so they can buy it and have a monopoly on long-distance telegraphy and telephony. And he didn't want to patent it, and he told them that it's all published, they can use it for free. But they didn't want it published and used for free. Of course, they wanted a monopoly, and they thought he's playing hard to get. And they kept coming back to him until he chased them away. And then they realized he's serious, so they actually paid a US inventor by the name of Michael Pupin to patent the ideas, to claim he invented them, and then they bought the patent from Pupin for a huge amount, and they actually paid a huge amount that nobody will question that these patents are really valuable. And that's one of the frauds in history of science. It irritated for some reason Norbert Wiener, the father of modern control theory. This story of the fraud irritated Norbert Wiener a lot, and he even published a book about it. And the book was fiction because Wiener was afraid he'll be sued by AT&T. But Wiener misjudged the fiction reader's taste, because the whole cover of the book is covered with differential equations, and that may explain why nobody picked it up, and the book is totally forgotten. It took me forever to find this copy. It was very, very difficult to find it. Okay, so this is a cable, and this is the receiver which was used to receive the signals from the cable. And the reason I know this is a receiver, because the cable actually ended up in Halifax from where it went by land cable to New York, and the receiving station was called the Halifax Depot, and all the equipment was engraved Halifax Depot. And you can see here, it's engraved Halifax Depot. So this was what's called a mirror galvanometer. That was the receiver for the signals. There was a little mirror, and when the feeble electric currents came from the cable, this little mirror moved and reflected the light on a wall. So the operator was watching the spot of light on the wall, and he could tell by the movement of the light if these are dots or dashes. And then he transcribed them by hand and retransmitted them to New York, because the signal was too weak to operate a Morse printer or even a Morse sounder. The only thing which could pick it up is this very sensitive instrument invented by Lord Kelvin. It's called a Kelvin galvanometer. But once it was transcribed, then you can send it over a normal telegraph to New York, because in New York they already had equipment like this equipment, which is recording telegraphs. That is a much later model, but you can see, you can turn it on, and you can see the paper coming out, and this is printing on the paper the message. So like the cases with so many inventions, not always the right people got the credit. And even with the invention of the telegraph, everybody knows about Morse. Now, Morse didn't invent the electric telegraph. What he invented is single-wire telegraphy. There was electric telegraphs much before Morse, but they all needed multiple wires. Some of them needed 1 wire per character of the alphabet. Some of them needed 5 wires. But of course, if you have to lay between cities multiple wires, the economics aren't there. But if you can do it with 1 wire, it's much more economical. So Morse invented a telegraph which only needed 1 wire. The current actually returned to the ground. So it was cheap to implement. What is strange that a couple of years before Morse, Wheatstone in England invented a very ingenious and simple 1-wire telegraph, which basically was totally forgotten because Morse was actually very good in business and in promotions, and Wheatstone was not. So this is actually quite a rare thing. This is a Wheatstone telegraph, and the way it worked is you have a transmitter that all what it does, when you turn it, it breaks up the current. And all what there is in the transmitter at the back, it's a little bit like the phone dial I showed you earlier. It has a wheel, and each click of the wheel breaks up the current once. So if you want to send, say, if you want to send a certain letter and it's a 5th letter, you turn it to the 5th letter and it breaks the current 5 times. The receiver is also very simple. You first zero it. So before you start the telegram, you send 1 pulse, which makes the bell ring. And if the bell rings, you know that you have to turn it to 0, say to top position or whatever. Now, once it's zeroed, it has a coil and a ratchet wheel. So each pulse of electricity moves it 1 letter. So if I move these 5 positions to transmit the 5th letter, this will get 5 pulses and move and show the 5th letter. So the nice thing about it, you don't have to learn Morse code because it spells out the text in plain English. It is 1 wire. It has the only disadvantage I can think over Morse that it needs more signals per letter. If you have 26 letters, which use between 1 and 26 signals, the average number of pulses is, let's say, 13, while with the Morse code, with dots and dashes, the average number of pulses per letter is maybe 4 or some number like that. But this is really not a huge limitation, because for land telegraphy, the speed of the operator was still the limiting factor. The speed of the electrical cables was fast enough. And in the transatlantic telegraphy, once people started listening to heaviside, again, the speed of the cable wasn't the limiting factor, it was the human factor. Or even if it was mechanized, that was the limit. So this is quite a rare piece from history of telegraphy, predates the Morse telegraph by a few years. So this would be about 1830 or some year like this. There's no date on it. So one thing which is interesting, that about 100 years ago or 200 years ago, people were much more optimistic. Because, for example, today, if a new chemical is invented or a new material is invented, people immediately research what strange diseases it can cause. And it's always regarded with great suspicion until many studies on safety are done. But 100 or 200 years ago, the attitude was opposite. When something new was invented, people immediately assumed that it's going to cure some disease. The only thing was to find the right disease it cures. But immediately people thought that there is no such thing that this great invention is not going to help somewhere. And there was lots of quack medicine because of that. I'll show you some examples. The first example is that when radioactivity, and especially radium, was discovered, and things were glow in the dark, people said that must be healthy or must be good to cure something. So there was a period, especially between 1920s and 1930s, that a lot of things with radioactive elements were sold to the public as being healthy. There was all kinds of radium drops, radioactive creams, and the most interesting thing that people believed that if you store your drinking water in a radioactive container, it's healthy. So here is an ad from the now closed, unfortunately, Museum of Questionable Medical Devices in Minneapolis. That was the name of the museum, and it had a large collection of things like this. So this is an ad for radium jars to hold your drinking water. Now, the interesting thing about it, and there is a whole book about this period, and the book is called Living with Radiation. So the interesting thing about it is the different vendors were competing how radioactive these jars are. They had to specify how many millicurie or microcurie of radioactivity they emit. And the FDA used to go around to the stores with Geiger counters and remove from the stores all the containers which are not as radioactive as they claimed. So it was strictly enforced. So this is a picture. Another picture or poster from the same museum is when people discovered tapeworms. They thought they couldn't be all bad. There must be some good use for tapeworms. And they were sold to ladies to lose weight. As you can see, this is an ad for sanitized tapeworms. Okay, it says easy to swallow. Okay. So another example from this period of optimism is this machine. Now, this is a high voltage generator, and the idea was that if you get an electrical shock, it must be good for something. Obviously, it can't cure any kind of physical disease, like a fever or a broken leg. So therefore, it must cure some mental diseases. So people used to sell these things to doctors to treat mental diseases. And what it was a high voltage generator. Okay? And you hold these two electrodes and you get a serious electric shock. Now, two things are interesting. First, there were thousands of those machines made, and all the ones you find on the antique market are totally worn out, which means they were used heavily. Even this machine, this was a top-of-the-line model, because in this one you can dial in the strength of the shock depending how bad your mental state is. So that was a very expensive model. So even this model, you can see the gears, everything is completely worn out. Okay, it has, actually it doesn't have the instructions here, it had some instructions which went with it, how to treat what they call nervous diseases. So this is from the good old days where every new thing was a cure. So in general, when there is money to be made, there is always fraud. And it's true in everything, including high tech. So until the recent story of Theranos, the biggest fraud in the history of high tech was the Keeley Motor Company. So this is something which is quite rare. This is a share of the Keeley Motor Company, which, as you'll hear in a minute, was a complete fraud. But the fraud was a very elaborate and long-lasting fraud. So John Keeley was a self-taught musician and mechanic in Philadelphia in 1872. And he came to investors with a story that he found a way to extract the atomic vibrations from water to make free energy. Now, free energy is a subject that even today YouTube is full of videos promising free energy, but nobody built it up to an operation the size of Keeley, although some came close. So Keely built a very strange machine, and he invited people to observe it and test it. And they should have been suspicious right from the beginning, because you can only start the machine by playing a certain tune on the violin, which is a bit strange, but somehow when they checked the machine, they couldn't find anything wrong. And the machine produced a lot of power. I mean, after Keely died, and that was many years later, people discovered he had an elaborate system built into the walls, which transmitted power to the machine from the basement. So they had some engine in the basement, which ran some shafts in the walls, which ran some shafts through the table, which drove the machine, and some other machines he had, which were supposedly connected to electric wires to measure the power. The electric wires were actually hollow, and they transmitted compressed air into the machines. Because he built different machines, and each one had a slightly different fraud in it. But the interesting thing is that, first of all, he managed to pull this off for 26 years. As I said, he started the scam in 1872, and it went on for 26 years until he was run over by a streetcar in 1798. Yeah. And during all these years, he was a respectable citizen, earning good money, being quite involved in charities, and in general, a very prosperous and respectable citizen of Philadelphia. Now, what he was going to do is going to build a car engine which can drive across the US on 1 quart of water. And he hired many engineers who designed all the parts of the car engine, and he himself concentrated on what he called the harmonizer, which is a mystical piece of the equipment which actually extracted the energy from the water, which he said is such a secret he doesn't want anybody else to know it. And this went on, and every year there was a delay. And at some point, the investors put pressure on him to show some results and get into production. And that was maybe 10 years later. And just when there was too much pressure on him to get into production, he announced that he invented a much better engine that can run across the US on a thimble full of water, like 100 times less water. Now, the investors claimed that a quart of water to cross the US is good enough and there's no point delaying. But he said that basically his scientific integrity doesn't allow him to produce an inferior engine which uses a full quart of water, where he knows you can do the same on 1 thimble full of water. So they went to court, and to everybody's surprise, the judge sided with Keely, saying that you couldn't force a scientist to compromise his scientific integrity, and the investors had no choice but to let him finish the second model of the engine, and again, which went on and on with all kinds of delays, and there were many people who suspected the fraud, and he had some rich widow, which was one of the backers, and she started wavering, and she wanted him to invite some known scientists to examine the engine, and he agreed. So he invited one person from a US university and one person from England. And the person from the US was skeptical, although he couldn't find where the fraud is. But he was skeptical that it really works the way Keely said. But surprisingly, the expert from Britain examined it and announced that it's a genuinely new principle, and there is no question there is a huge invention here. And this gave him another few years. At the end, he was run over by a streetcar, and after he died, people took his house apart and found the fraud. So basically, until Serrano's, Keely Motor Company was basically the place to refer to when you looked for a high-tech fraud. And strangely enough, there is a place in the US which sells you all kinds of shares of extinct companies. And to my surprise, they had Keely Motor Company shares. And here it is.